Good morning, everybody. Let's get started. Today, I'm going to start one of it's a two-part lecture on the technology to solve the carbon and climate problem. And of course, we're talking about this amidst the backdrop of COP26, which is going on and producing the, well, at least by me, the expected level of non-binding commitment to 1.5 degrees. This object on the front here, anybody know what that thing is? Somebody? Yeah. Yeah, it's a tokamak. It's a specific type of fusion reactor that is called a stellarator, whose design was conceived of here. And one of the reasons I like it is it's the first object I'm aware of that was designed with machine learning. The shape of the containment vessel there is an asymmetric, almost biological shape that no human mind could have come up with. And it's a machine learning algorithm that figured out how to do it. This is a configuration for a stable fusion containment that doesn't succumb to the mathematical chaos that is turbulence in these fluids when they get really, really hot and really, really dense, right? So anyway, I put this up here, not because it's going to be, in my view, a solution to the carbon and climate problem, but because it isn't. All right, this is a device that exists at some level, but it is a long way before it becomes a practical power source. The claims of the now several startups in this space notwithstanding. They're smart people, but this thing is a long way off. If I had to guess, I guess that it ends up in a spaceship as its drive before it ends up in a power plant to giving you electricity. Not that you couldn't make one. You could probably make one in, I don't know, 10 years with a crash program. It's just the electricity would cost so much money relative to the other non-emitting sources that we have. All right, so if I were emperor of the world, I don't want to denigrate fusion. I would do more fusion research, not less. But it would be but it wouldn't be to solve the carbon and climate problem, okay? It would be because I think it's cool and we're gonna use it someday, I'm sure of it, for something. So I wanna talk about where, today, in fact, just in the last couple of hours, a full draft of the COP26 agreement has been leaked, and its cornerstone is a strong commitment to 1.5 degrees. Strong commitment doesn't mean a binding commitment. It means that all the nations are supposedly going to sign on to the idea that 1.5 degrees is something that we need to stay under, and that's tough. That means globally, as you know, stopping emitting as a species approximately at mid-century, which is 29 years from now. Less than the lifetime now of a gas-fired power plant. So, I mean, this is a titanic job. It's one that I suspect we won't actually achieve, but I do think we'll get moderately close, all right? And maybe, who knows where technology is going, but this is really a stringent goal. I mean, it's an incredibly stringent goal. Not very long ago, even at the beginning when I started teaching the Nexus class, and I've only done it 5 freaking times, people were talking about getting started in the United States, not getting finished. And so how did the goalposts move so rapidly? All right, because they really have. Globally, the goalposts have just galloped. In Paris, they galloped to 2 degrees, and now they've galloped to 1.5. They can't gallop any closer because we're so close to 1.5 now, right? All right, so what happened? Now, 17 years ago, a guy named Rob Sokolow, who some of you may have run into, who's an emeritus professor, and I published a paper which was viewed as revolutionary at the time. it's been cited like thousands and thousands of times. And there were some of the early climate treaties were based on this thing, on the scheme, and blah blah blah, right? And I put it up here not because I'm nostalgic about it. In fact, this has been talked about to me so much over my life that it kind of gives me a gag reflex whenever I see that diagram. I mean, it's kind of, you know, yuck. But the reason I put it up is to show you that something that we produced 17 years ago when you were little kids was just viewed as revolutionary. And today it would be viewed as unbelievably inadequate, all right? So in 2004, we were trying to make this problem simple. We noticed that, you know, approximately there were linear growth in emissions. And so we said, okay, business as usual is just a straight line. And we went out 50 years because more than 50 years was to a technology that we couldn't envision. And it is true, you know, in 2055, we might have a functioning, commercially deployable fusion reactor around, right? And we don't know. We might have photochemical fuels, a panel you put on your roof that intercepts the CO2 that's blowing by and uses the energy in sunlight to turn it into a fuel like dimethyl ether that you burn in your furnace and in your stove, all right? And so an artificial photosynthesis machine on your roof, you know, so we don't really know what's out there, but we can kind of envision the terrain in here. And we said, look, let's just suppose that instead of climbing like this, global emissions were to be frozen for 50 years, okay? And then subsequently, maybe they would start to decline. Now this trajectory would take us to a lot, 3.5 degrees, 4 degrees, something like that. It was viewed as unbelievably stringent at the time. And you can think of it as a trajectory that was designed to get us in mid-century, somewhere around 500 ppm or something like that. And so the idea was to try to say, can we cut out this green triangle from the future emissions path? Now the people often asked me, you know, over the last almost 20 years, who was the audience for this thing? Because it turned out that there was quite an audience for it, right? But when we wrote it, there was an audience of one person. It was George Bush's Secretary of Energy, whose standard speech was that we lacked the technology to get started on the climate problem. They'd run through, there is no climate problem, and now they were trying out, we don't have the technology to get started. And the sort of tagline was that we need a revolution as fundamental as the discovery of the uses of electricity by Faraday in the 19th century to get started. And so what we wanted to show was that, in fact, we had the technology to get started that was deployable. And later on, I saw the guy, and he said, first thing he said was, "You wrecked my speech." All right, we actually worked. It was the only paper I have probably that actually ever worked for anything, right? So it shut that speech up. In any event, we said we want to cut this triangle out, which went from 0 gigatons of carbon, not CO2, of carbon emissions per year, to 7, which were today's current, which were the then current emissions, over 50 years. And so we divided these 7 gigatons of eliminated emissions into 7 different wedges, and then asked, are there any technologies in the marketplace back then that could meet those seven wedges, and discovered that there were 15 different technologies already in the marketplace at scale that you could do. So the answer was, of course, you could get started. We had redundant, we didn't even have, you could let the marketplace decide among 15 alternatives for 7 wedges, right? And some of the technologies could do too. And so why do we focus on a path this unstringent? Well, in part to shut this guy up, but also we actually didn't have the technology to even talk about finishing the job. What we were trying to show is that we had the technology to get started. So 17 years ago, it was news, big news, my most cited paper ever, that we had the technology to get started. And now with COP26, all we're talking about is how to get finished over a shorter period of time than we were trying to get started here. So that's the point. For that to have happened, something had to have changed. And what was it that changed? So this was the emissions consistent with the Paris Agreement. That was sort of business as usual, given the deployment. I think this is 2017 from UNEP. This is a 2-degree scenario. We're just below 2-degree scenario, where net emissions in red here go to 0 around 2085, right? The blue are negative emissions, done with a bunch of different methods that we'll talk about, not next time, but the time after. Green are mitigated emissions. See, the light tan is residual CO2 emissions. You see there's still some CO2 emissions out here. And the darker tan are non-CO2 greenhouse gases, primarily methane and N2O. And so this is a trajectory that we were talking about at the Paris Agreement. And so at the time of Paris in 2017, people already thought, you know, we have enough to sort of get this green thing out of the market and create this blue thing down here, this negative emission. And that then will drive the emissions down to 0 in 2085. And now today, we're talking about all the nations of the world, at least verbally committing to 1.5 degrees, which puts net zero forward to here, right? Much steeper cuts. And in fact, this is the IPCC 1.5 degree report. These are a bunch of different scenarios about the way to get to net zero, with different amounts of negative emissions and different rapidities of cutting. And the important thing is that different scenarios for reaching 1.5 degrees all cross 0 at about 2050. The problem is so constrained that you basically, 1.5 degrees means we stop emitting as a species in 2050, full stop. I mean, you could conceivably do it some other crazy way, but you can't tell a story that passes the laugh test unless you stop at 2050. And it's because we're so close already. All right, so net zero is in the air. When I made this slide up, the COP agreement had been leaked. Biden had ran on 2050 net zero with 80% non-emitting electricity by 2030 and 100% non-emitting electricity by 2035. With electrified vehicle fleets, largely by 2035 and a few other measures. China, several months ago, not quite a year ago, the government committed itself to 2060 net zero, which is actually a pretty big deal given the size of the rural population that's still in China and their deployment of coal as a fleet. They've announced very recently that they're going to be deploying really large quantities of advanced nukes, which is an interesting experiment. It'll be the first time that nuclear electricity technology has advanced substantively since the early 1960s, all right? India, Modi and his government announced in advance of COP that they were committing to net zero in 2070. Now, 2070 is a ways off. You could turn your nose up at that. But actually, to reach 2070, you've got to actually be thinking about it now, because some of the assets that you're building now, particularly coal-fired power plants, you know, they live 50 years. And so you've got to really be thinking hard about what infrastructure you're deploying in the next 10 years. And so his party certainly has ambition to remain in power. And so I do think 2070, now 2070 for India is not consistent with net zero for the world in 2050. But I do think it's realistic for India, right? I mean, India still has massive numbers of people in poverty. And the question is, will you be able to bring them out of poverty fast enough, relying only on renewable deployment? All right. India lacks what's known as a firm source of electricity other than coal. And so we'll talk more about that later. In any case, these numbers I think are pretty amazing. Basically, every developed nation in the world has a 2050 goal or sooner. And now the biggest of the BRICS have a 2060 and a 2070. This really means that the developing nations, the leaders of the developing nations, think that the developing world even can come into zero somewhere just after mid-century. And so I do think it's realistic to think that, yeah, okay, we may miss 1.5 degrees, but if we can pull this off, and technologically we could pull this off, right? We might be in at 1.6 or 1.7. It's not like disaster land here. Now, there are more stringent calls, all right? This is a group called Extinction Rebellion. Extinction Rebellion is a hoot. Who has anybody ever seen Extinction Rebellion at work? Anybody from the, like, yeah, there's one from London or you know. Extinction Rebellion had a thing for a while where they were gluing their butts to like the doors of corporations, so like, you know, headquarters of fossil companies and stuff, and super gluing them. It was amazing. Anyway, yeah, but this is their sort of manifesto. They have 3 demands in the UK. The first one is that the government must tell the truth by declaring a climate and ecological emergency, working with other institutions to communicate the urgency for change. Number 2, act now. Government must act now to halt biodiversity loss and reduce greenhouse gas emissions to net zero by 2025. Okay, no more emissions in 4 years' time. All right. And number 3, government must create and be led by decisions of a citizens' assembly on climate and ecological justice. And so, so that's a pretty radical proposal. Basically, I mean, who's in that assembly? So there are radical groups now that are attractive to a certain segment in the population that want much more stringent action. Action that is so stringent that I'm not sure even on a wartime footing, right? If you did command and control from an ironclad dictatorship, you'd be able to pull off. So there are certainly forces tugging us faster, but this 2050 net zero seems to be the locus that has attracted the nations. And so why is that? What's going on with that? Why 2050? So before I do that, let's do a little bit of clicker stuff. How do you assess the chances that humanity will be able to reach net zero by 2050? I want to see. I mean, I've told you what I think, but I want to just get a little bit of response here. There are going to be a series of these, so just like vote real quick. All right, and if you miss one, don't freak out because there'll be a next one and the next one. Right? Okay, that should be enough. So in the middle, right? I guess I would be C, pessimistic, but I think it's possible, right? I mean, you know, you don't know what technology is going to do necessarily. So I agree with all of you on that. Okay, next one. Did I just end it and then poll? Other one, yeah, okay. Okay, how do you assess the chances that any of the top 20 emitters will be able to reach net zero by 2050? This is not the globe. This is like the United States, this is like any single one of the top 20 emitters will reach net zero. So will the United States is one of those, obviously. What do you think about that? B, optimistic, and A, very optimistic. Yeah, I'd probably be with A. I think that somebody, you know, a Germany or somebody is going to reach it, right? One way or another. Okay. So, oops. Is this another one already or not? Oh, it is? Okay, good. Well, I better get over it. Oh, so I get that's enough for now. That's enough for now. Put it away. Okay, so why did the goalposts move? So as I said, 17 years ago, it was big news to get started over 50 years. And now everybody's talking about getting done in less than 30 years. And even the developing nations have jumped from, you can't talk to us about reducing our emissions, to we could be done in less than 40 or less than 50 years, right? Less than the lifetime of a coal-fired power plant in the case of India. But why did the goalposts move? Well, some may argue that it's because we discovered that the climate problem was much more severe than we thought it was, and that we were close to a tipping point. I think that if you polled people who were concerned about this issue in the US and Europe, that's the answer you'd get. That's my guess, is that we discovered we're really close to a tipping point. It's really scary. All right. But instead, you know, we've talked about this already. As far as we can tell, the tipping points, other than this multi-thousand year rise in sea level, right, is quite far from where we're planning on quitting. All right. The tipping points happen up here, not sort of down here. Now, we could be wrong about that, but and I don't know, climate scientists are freaked out about quite a bit, but I don't know anybody who actually thinks there's going to be some really crazy tipping point right nearby. And, you know, the loss of a major ice sheet, or, you know, mass extinction, or the thermohaline circulation stops, so that all of a sudden you have a bunch of years in a row in which agriculture can't happen in the tropics, or, you know, something terrible. Really, really, really terrible. So I don't think the science points to there being a tipping point close. And in fact, this is from the IPCC 1.5 degree report, where it shows 1.5, 2 degrees. And then the color indicates how severe the risk is, okay? How severe the risk is. And this is not, this is actually done with so-called expert elicitation. They go and ask like thousands of experts, and this is sort of the consensus view of the experts. That doesn't mean that this is true. It just means that it is an extremely accurate reflection of what the scientific community thinks. And what you can see here is that there is no conspicuous thing that is changing really rapidly at 1.5 degrees. You know, this is going from white to yellow, which is low risk for mangroves at 1.5 degrees. Fluvial flooding, you know, mostly this is a continuous problem. We have accelerating damages, all right? And so we know it's getting worse and worse and worse, but there's just no evidence that there is a discontinuity, an abrupt discontinuity that we're trying to stay under. There's no scientific consensus for that, even though I do believe that the public might think that. Another option might be that somehow the public just woke up. And I think the public has woken up, but I actually, my own personal view, and this is an opinion, not a fact, is that the reasons the goalposts moved is the technology got cheaper, making the political goal feasible, all right, for at least half the people in government. So all of a sudden, everybody started hearing that this could be done without significant cost. And that was a new message. And I think as soon as people heard that this could be done without significant cost to them, they thought, well, why don't we do it? And then you can get sort of positive feedback going. So I think the reason is the technology got cheaper. And I want to demonstrate that now, because the technology did get cheaper, and the pace of technological change in the energy business was faster over the last 15 years that at any point, I think probably in history, although you could argue at the very beginning of the Industrial Revolution with the increased efficiency of steam engines, that was a more significant societal transformation. But there's been nothing like it in the lives of anyone on the planet who's alive today, all right? Whereas your lives coincide with a period of absolutely unprecedented technological change in this space. And it's really a testament to human ingenuity. It's possible we just got lucky, but I don't think that's the case. And you'll see why. Okay, so if we think about this as a horse race, let's start the horse race in 1990, and then we'll take a look at it in 2020, and then we'll take a look at it again in 2050 and ask where we think the technology was. So at the beginning of the horse race here, in 1990, we had a bunch of technologies on the map already. Afforestation and reforestation, planting trees, was already part of the United Nations Framework Convention on Climate Change, had just been added. So we knew that we could suck a little CO2 out of the atmosphere by planting trees. There's a lot of talk about it. Nuclear, we knew we could do nukes. I mean, we had more nuclear deployment in the US than anywhere else in the world. And France had just done a crash program of nuclear builds that per capita was larger than anything and is of the pace that we're talking about for the technological deployment and change in renewables over the next 30 years. They did a really fast nuclear build. Biofuels were in the air like crazy back then. It's primarily there because of an energy security issue, but that was when ethanol crept into gasoline. All right. And, it was farm subsidies. There's all kinds of reasons for it. But the fact of the matter is big companies were investing in trying to make biofuels better and cheaper. Wind and solar were in niche markets. They were many-fold more expensive than fossil. Not just like twice as expensive, like more than 10 times as expensive. But in specific locations, where you couldn't get the fossil too easily, there were, little wind turbines, and there were little solar panels on remote locations. There were solar panels on satellites. And people had them on their house if they were sort of aficionados. There was, for some reason, a lot of talk about hydrogen. Hydrogen can be made by a bunch of different ways, and we can talk about that later. But the automakers in particular were interested in hydrogen, and they thought maybe it was going to be the fuel of the future. And so there was a lot of research on hydrogen, but there really wasn't much deployable. Avoided deforestation was already a big deal. I mean, we knew this was something that was important for biodiversity and also had big carbon consequences. And improved efficiency, insulating your house, the advantages of that were all widely known. So this was the toolkit back then. And there really weren't front runners because nobody was in a hurry to deploy. The question was, were you even going to get started and when? That Wedge's paper was 14 years after this, and it was still news that we had the technology to get started. Everything was expensive, nothing was deployable, and then subsidies worked. All right. Now, what do I mean by subsidies worked? These are the subsidies in US dollars in the United States for nuclear energy and renewable energy and fossil fuels through time. And you can see that it, reached a lull back in the 1990s, but every year there were subsidies for renewable energy. And there were also subsidies for fossil fuels. And there were also subsidies for nukes. There were subsidies for everything. Congress was showering, and the administration was showering, all the administrations, liberal and conservative, were showering industries with gifts to purchase political patronage, and then with the rhetoric of energy independence and increasingly some talk about climate. These are tax preferences by type of fuel in 2016. And so this is end of the Obama administration. Renewable energy at that point was getting most of the subsidy. Energy efficiency was getting some of it, and fossil fuels some of it. We talk about fossil fuels as getting huge subsidies, and they do get huge subsidies, but in fact, renewable electricity gets more. Nukes, it's fallen off, right? So nukes, the bloom came off the nuclear rose in the United States some time ago. And we weren't the only ones. These are subsidies in euros from European countries for all kinds of different technologies out there. So the point is that not just the United States, but China and the EU and Japan and everybody were showering money on all kinds of technologies. And what did that do? Well, you concentrate the money per watt, for instance, produced until the technology in subsidized form can enter the marketplace, all right? And there's only so much subsidy, so there's only so much that it can enter the marketplace. But basically, you give it money and an unfair advantage until it can be traded profitably relative to other alternatives that are cheaper. And that causes a market to exist. That's what subsidies did there. And there were multiple firms that were competing for that subsidized market. And what capitalism does really well is drive costs down. And so those firms drove down the costs. Now, it's also true that there was research and engineering departments and in the Department of Energy. But if you kind of look at what really carried the water for cost reductions, it was market competition allowed because of subsidies. And one of the things I love about that is that you don't hear that anywhere. Liberals talk about subsidies and conservatives talk about market competition, and the track record that worked was the combination of the two, okay? Subsidies unleashing market competition. So here's the story with solar. This is actually data from the UK, but per installed watt in 1975, it was $100. And by 2015, it was something like 60 cents. And now it's something like 30, okay? Halves every 3 years. So it's something less. Yeah, it was 61 cents. It's under 30 cents, like a quarter now. That's a Moore's law reduction. If you put that on a log plot, it's a straight line reduction. And that one, that particular one there is over 40 years, but the track record extends to, well, 2021 now to 46. And so this is caused by the deployment and more firms competing against one another. As the price goes down, the subsidies go further, you get more deployment for the same, because no longer $100 on each watt, it's like $30 on each watt. So you have 3 times as much if you have the same total subsidy pie. And you end up with relentless cost buy downs, okay? And so subsidies worked. Subsidies with wind and subsidies with solar worked. And as they did, both of them, price just fell and fell and fell, and deployment went up and up and up. And not just in the United States. There were periods when the US almost dropped out, but there was always Germany, or there was always China, or there was always somebody else that were subsidizing. And so the firms had a market and could keep moving. So just during the period from 2009 to 2018, the cost of solar declined 76%, the cost of wind 69%, and the cost of lithium-ion battery packs 85%. There were also other revolutions. The only fossil revolution, basically all the fossil subsidies and the nuclear subsidies didn't work, okay? Like nukes didn't get better. All right, they just became more expensive and they kept blowing up, and it's like bad trouble. Fossil coal got a little bit more efficient, but what really changed, what really happened, what lit up was natural gas took off. Fracking came into the United States, and was invented exactly in the same way. There were tax credits for unconventional gas exploration. And there was a family, a single family in Texas who just kept poking around at this, using the subsidy to keep going for about 20 years. And it got better and better and better. And then finally, all of a sudden, they had the cost down to where their gas could compete on the open market against unsubsidized gas. And so they started to hydrofrack and horizontal drill. And what they do is they drill down and they drill a horizontal hole. And then they put some secret mix of usually very bad chemicals down the hole. And then they pump water in the hole at pressure until the rock fractures. And that then lets gas out of the shale formation. Subsequently, they discovered that oil comes out the same way, and the United States became energy independent as a result. And the total net benefit to the consumer from this payback and the solar and wind payback is a large fraction of the cost of the global economy. So those subsidies have returned value to the American consumer that are better than anything else just about the economy. Maybe early stage Tesla or Apple, you would have done better. But this is really a spectacular payoff. You hear in the news that subsidies don't work and they failed. There was probably a little before your time, but during Obama's bailout, there was a firm called Solyndra that you still hear about in Congress. And what they don't talk about is that an even bigger loan that went to Solyndra went to a firm called Tesla, and it would have gone under without that, all right? And so the net value to the American economy from those two loans, one of which wasn't paid back and one of which turned into Tesla, right? So this is the same sort of story here. Whether or not you think this is a good deal, that we have unconventional gas, it's actually, I think, a bonus, because we'll see in a minute that it does provide the US with a way to get to net zero over the short term before we invent something that we haven't invented yet. So now gas, solar, and wind are driving coal extinct in the US. Renewables are cheaper than fossil, over 2/3 of the Earth's surface, and will soon be cheapest everywhere, all right? There are places where, the wind doesn't blow very much and it's kind of cloudy all the time, right? And in those places, fossil is still cheaper. But every year, the fraction of the Earth in which wind and solar are cheaper than any fossil source of electricity gets larger, right? And it currently, of course, covers the entire United States. All right, so I got a bunch of different estimates of the levelized cost of wind and solar and coal and gas power. I think I'm going to show you this one. You can look at the other one too. I just wanted to indicate that there are multiple versions of these. All of these are produced by trade groups, all right? These aren't produced by advocates, not advocates for wind or solar, not advocates for nukes, not advocates for fossil. These are trade groups that try to give advice to energy investors. And so it's the caliber of their advice. They have to be dispassionate brokers of information. And these are their cost estimates. I think these are 2019 data published in 2020. And so the renewables will have come down substantially then. But let's just look at these numbers. The bars represent the range, the high to low range, depending on where you deploy it. These gold stars for nuke and coal represent the cost of running a plant that already exists, that you've already paid for, okay? So this is like you've got some plant on the ground. How much does it cost just to operate it? This star here is offshore wind. That number has come down a lot as floating wind turbines have advanced by leaps and bounds just over the last 2 years. Now, here's the story, right? So you've got PV on utility scale going from 32 to 42 and wind going from 28 to 54. And there's coal 66 to 152. And even operating a coal plant you've already paid for, and a lot of the market with these 2-year-old data, you still had cheaper solar. You could put in new solar. It's cheaper than operating a plant you already had, okay? And so this is the story, right? Gas combined cycle, a combined cycle gas turbine. So a coal-fired power plant, what it does is you boil water, the water rushes out as steam, the steam goes through a turbine, the turbine spins a generator, and that makes electricity. That's what the steam turbine, it's a steam engine, all right? A natural gas fired power plant, if it's a combined cycle, what it is a jet engine. A lot of these are literally commercial jet engines that you cut the compressor stage off, like a 777 jet engine. And it's tied, it's just like a giant home generator that's run by a turbine burning natural gas. But in addition to the fire and the jet engine spinning a generator, you also collect all the fire that comes out of the back of the jet engine, and you use that to boil water. And then you make a steam turbine out of that. And so you get 2 shots at the energy. And so it's much more efficient. When they talk about a single cycle, single stage turbine, that's just a jet engine powered generator. Combined cycle means jet engine plus you use the exhaust from the jet engine to boil water and have a steam turbine too. And so these, for new builds, are cheaper than coal, and that's why coal's going extinct. That was the first thing that drove coal extinct. But wind and solar are cheaper than combined cycle electricity. Also, one other thing that's really worth knowing is that, another thing, nukes. You hear all kinds of politicians talk about how great nuclear energy is and how expensive renewables are. It's like nothing could be further from the truth. Nukes cost a fortune, all right? You need 125 people, 24/7 in a gigawatt-sized nuclear power plant to like watch everything. You need 5 in a combined cycle power plant of the same size, all right? And so in addition, the construction of the containment is very expensive. And so the capital outlay that you need to build a nuclear plant is very high. And we might be able to do better, and that's what the Chinese experiment is all about. But nukes right now are really, really expensive. So the idea that this is a solution that's practical and one that's right in hand, well, yeah, if you want to pay something that is, almost 10 times more in cost. The other thing is that putting solar panels on your house, although I love it, it's like it would be cheaper to build a nuclear power plant, all right? The point is that it's really expensive. Everybody loves the idea, oh, we should have distributed solar on everybody's rooftop. It's a big deal in California. Everybody wants to have distributed solar, not big corporations running the solar. And the fact is that it's really expensive to do that. All right, that's just what it is. And so if we're going to have a public expenditure to sort of goose this along, is it sort of ethical to distribute that to homeowners, or should we in fact do something far cheaper? There is probably something intermediate we could do that almost no one is talking about. All right, there are few people that talk about it. I talk about it all the time when I'm in Washington. A lot of the land in the US is owned by the federal government or the states or municipalities. By area, the federal government owns something like 40%. I mean, it's a lot, but most of it's the West. The states own 9%, and municipalities own 1 or 2%. But it turns out that you don't need to cover very much of the US with solar to power the country, right? And the people who own the land own the wind that passes over it, and they own the photons that hit it. And so there's no reason in principle why governments, local governments or state governments, couldn't build facilities and use the revenue from those facilities to provide the government services instead of taxes. So of course, it's a form of socialism, right? Local socialism or state socialism, because it's the government owning something. But at least in principle for towns, this could be a real godsend and could actually create pull for these technologies into towns, especially, because most towns don't have an energy business. The energy extraction is concentrated in just 3 areas in the United States. Whereas if we deploy wind and solar everywhere, every town is an energy producer, and that creates jobs, but it could also create revenue and commercial deployment. On the land outside of town, you build a commercial looking facility, but the revenue flows back in to buy the police uniforms, right? Whatever. Anyway, that's what's going on there. And this graph is the revolution, because 10 years ago, with this being 10 times more expensive, those costs were out here, right? And 20 years ago, they were over there, right? And so this is the thing that's happened. Nobody else moved down like that, right? It was wind and solar that screamed across this graph during your lifetime and lodged now at the bottom of it, and they're still headed down. The current energy system, I don't even know why this is here, but so you will not be tested on this diagram, okay? But if anybody wants to look at it, this shows our current energy system, and these are the producers, and these are the services that energy provides. I think I put this in here to introduce the idea of energy services. When you design a net zero energy system, what you do is you try to design it to provide energy services that the public expects. In Europe, there's still a big push to try to convince the public to expect fewer energy services, all right? To make their house colder and stuff like that. We've given up in the United States. Basically, we've decided our population is pretty piggy and they just want what they want. And so we're going to deliver what they want without emissions. All the designs you'll see later in this 2-part lecture are predicated on that. And these are the services, existing services the public is expecting, and our current energy system provides those services in that way. And I don't expect any of you to memorize this, but if you want to know how our energy system works, that so-called Sankey diagram, that piping diagram, really shows you where it all comes from, all right? Where the heat comes from, what fuel, and blah, 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 how big it is. All right, so we'll start next time at 2020, where the horse race looks far different. You see wind and solar here now are out front. And nukes are kind of trailing, and so on. So next time, to be continued.